Hi, this is Dan Bullard, retired electronics engineer, out on the river again. I'm at, I think it's Fort William Bend. I don't know. Little Ambition's back there. You'll see it drifting around. I got this really cool anchor buddy system that I use so I can keep it offshore and it drifts around out there and I don't have to worry about it. At least I don't think so. Anyway, I want to talk about DSP, digital signal processing. My very, very favorite thing. I used to do digital test at GenRad, and digital test was fun, interesting. I did all kinds of things, memory, and I even did the chip for the SETI project, which was cool. Well, I didn't do it, I worked with it. But then I went to what became Credence and started doing mixed signal because they needed somebody to do mixed signal. And nobody knew mixed signal. And neither did I. But, you know, it's one of those things. You do what they tell you to do. So I did it. And it was just astoundingly wonderful. I just love mixed signal. Now, remember, I was no good at math in high school. I was terrible. And so I got through, I tried to get through this stuff, and it's like, it took a bit of work. But I did have some college, and they talked about sine and cosine and stuff like that in college, so I knew something about that. I had a customer, believe it or not, HP in Boulder, Colorado. They wanted to buy a tester. So the salesman hooked me up, and I flew out to Denver, drove up to Boulder, not too far from Denver, and talked to the customer and this manager there, and I said, you know, okay, we make a cheap box, but why do you need our tester? You guys have the HP tester, the Agilent, whatever it's called now, the 83,000. And he said, it's too expensive. We need a cheaper machine. I said, okay, fine. So we looked at all the stuff, we looked at all the requirements he needed, and they all seemed to fit. But they left one out. So our Filipino subsidiary sent an applications engineer, Marvin, not the Paranoid Android, the other kind. They sent Marvin to the U.S. to work on this thing. And I was standing by in Oregon in case Marvin needed help. And Marvin did great. He got everything set up. He got the load board built. He was writing code, and he finally got to a test they didn't mention, which was a duty cycle test on a free-running 700 kilohertz clock that came out of the device. And so I'd done that previous article that I talked about in my previous video. Back in 2005, I did an article on how to test very high frequency waves. So 700 kilohertz is no big deal, right? I'm just going to measure duty cycle. And I'd used TMUs in the past, time measurement units, and I knew what was involved and I knew all the stuff, and so it was no big deal, right? So we coded it up, sent it off to Marvin, and he reported back that it didn't work. We're like, what? Me and Steve Holder were like astonished. It didn't work. Because we beat up everything. Pretty much, all you have to do is take a digital pin and capture just the ones and zeros with a 50% VOH, VOL thing, so that it crosses the threshold for VOH and VOL at the 50% point of the wave. And then you can measure duty cycle very easily by taking the average, the DC average of whatever you capture. Now there's some error involved, and our goal was to get rid of the error. But the error is very small, right? Because if you capture, I think we captured 1376 cycles of the wave. So 1376 plus or minus one cycle, and you take the DC average, you're likely to get pretty close to the real answer for duty cycle. But we were trying to eliminate all the error. So we wrote this code, we sent it to him, and it didn't work. He reported. So we said, okay, well, Marvin, send us the wave that you captured. So he sent us the wave, and we had to experiment. And we came to find out much, you know, when you listen to your professors, I swear to God, this is true. When you listen to other people, they'll say stuff like, oh yeah, square wave, you know, the second harmonic is not there, and the third harmonic is 1/3 the amplitude of the fundamental, and the fifth harmonic is 1/5 of the amplitude of the fundamental, and so on. You believe that stuff, right? Well, that's only true if it's exactly 50% duty cycle. And since we were measuring a variable duty cycle signal, all bets are off. But we didn't even think about that. We were just listening to what our professors or other people had told us. So we started looking into it to try to figure out what was going on. And one of the problems was that we captured 1,376 cycles, 0.25. So we captured a quarter of a cycle in this example. Okay, so 1376.25 cycles. Well, that was interesting. So the fundamental is a bit attenuated because its energy is more spread out. That's why we do windowing in some cases. But we weren't going to do windowing. We don't care about that stuff. We don't want to take the time to window. We simply want to look at the fundamental frequency. So the problem is the first harmonic, the fundamental, is 1376 cycles. The second harmonic is double that. The third harmonic is triple that. And the fourth harmonic is, I think it was 5505.0 cycles. Okay. Now that means that all the energy for the fourth harmonic pops up and none of it's spread out. And that made it taller than the fundamental. Oops. So our thing that went and looked for, our algorithm that went and looked for the fundamental, was seeing the fourth harmonic as the fundamental, which was a mistake. So we did a thing where we found out what the fundamental actually was by doing a gross. In that last video I talked about Barry Culp, not Robert Culp's brother. Barry Culp was an applications engineer for Credence, ended up being an applications engineer for Maxim. Maxim Integrated Products, not Maxim the girly magazine. So we used Barry's technique to estimate, because it's only good at estimating, to estimate where we would find the fundamental. So we found it at 1376, more or less, and then when we did the FFT, we could go look at 1376 or in that area and find it, ignoring the fourth harmonic. So once we found that, then we used a function called Bunneman, and that's a really cool function that tells you how many partial cycles we have. Like I said, you may not know how I know that I got 1376.25. Well, I know that because I ran the Bunneman function. Now, there was another function on the Credence VistaVision called Sine Curve Fit, which would also tell you the approximate partial cycles of a wave. But Dave Reynolds, my buddy Daver, that I'd mentioned before, he had come up with this thing called Bunneman. He does all kinds of crazy stuff. He does Diophantine equations. He does all kinds of crazy stuff. So he came up with this Bunneman thing, and Bunneman told us, just by looking at the two highest bins in bin 1376 and bin whatever is nearest that in this wave, what the partial cycles is. So it was 0.25. Now, we took 131,072 samples of the wave. So that's basically 128K. We took 131,000 samples. Now, because we know we took 0.25 cycles, we can do the equivalence thusly. and we can calculate how many samples we need to chop off. We need to chop off enough so that we only are left with 131,048 samples. Now that contains an integer number of cycles of the wave. So now we can take the DC average of 131,048 samples, take the DC average of that, and that'll tell us the DC average, the duty cycle of the wave. And this was accurate to 200 picoseconds. Now remember, the overall timing accuracy, OTA, of a digital tester is related to the digital drive edge and digital capture edge. And on that on that Nexus tester, that was about 2 nanoseconds. So the OTA was about 2 nanoseconds. But my technique got us to a 200 picosecond accuracy. 200 picoseconds from a tester that's rated at 2 nanoseconds. That's pretty goddamn good. Okay, that's just one thing you can do with DSP. I want to mention another one that I did. I got an article published in Evaluation Engineering. That was a magazine way back when, and you can still find it. The article was called "It's All in the Noise." And again, Connie Gray Beal was the publicity gal, and she got me published in Evaluation Engineering with "It's All in Noise." And the idea there was I was going to measure the roll-off of a filter with something that I came up with based on periodic white noise. I had tested a filter back on the STS 3000, which was a early Credence product. And somebody asked me when I was teaching a class on the STS 3000, what does the roll-off on the telecom filter look like? And I'm like, I don't know. Now, when you ask an instructor a question, he's supposed to have an answer. And if he doesn't have an answer, he's supposed to get you an answer. And so I took it on myself to get the answer. So what I did was I wrote a function in time domain. I wrote it in time domain and then changed over to frequency domain, so that what I could do is I could go and generate a 1 kilohertz wave, and then a 2 kilohertz wave, and a 3 kilohertz wave, and a 4 kilohertz wave. Basically, I generated in frequency domain a straight line flat response from 1 kilohertz all the way up, I think, to 23 kilohertz. Now, I knew that that wasn't going to work out because there's a roll-off and stuff. The AWG had a roll-off and all that stuff. So what I did was I sent that out through the tester, bypassing the telecom filter. I brought it back, I did the FFT on it, and I looked at the roll-off. Then I took the roll-off that I got and I did an inversion. Basically, I took the reciprocal of that roll-off. So invert it, take the reciprocal, and that generated an upslope, and I used that upslope to multiply against my frequency domain wave, my frequency domain response, and then I could run that out again, and I'd get a totally flat response, totally flat. And then I could kick in the telecom filter and look at the roll-off of the telecom filter in the 8-pole mode or the 4-pole mode or the 6 and 2 or whatever. It was great. It was friggin' great. And I use that as an example in my DSP course for the STS 3000. And I think, people got something out of it. I had a lot of students who had to take my class and go off and do real parts. And I always got good feedback from them. Well, this periodic white noise thing was kind of a tweak on that. Back at Credence, back in the olden days, Paul Botsford, who was the expert at this stuff, and very intimidating for most people, Paul Botsford believed that you could use an impulse to measure filters. Well, you can't. The impulse has no energy, and if you make it wider so that it has energy, you change the roll-off. It actually has a roll-off now. So a single impulse has an absolutely flat response, and I talk about that in my books, Distortion and Harmonics. It has absolute flat response, but if you widen it so that it has some energy, it starts to roll off. It starts to have a curvature to it, and you can't have that if you're testing a filter. Now, Paul Bosford seemed to believe that the impulse was the way to go, but you're going to pick up noise, and the noise is going to crush your impulse values. So Daver, my buddy Daver again, he wrote the waveform functions for the mixed signal wave tool on the next test. And I was going through them, and there was this one called periodic white noise. And I said, Daver, what is that? Periodic white noise. And he says, oh, that is white noise. It's absolute flat noise, but it's coherent. I said, oh, so I could use that for a filter. He says, yeah, that's why I made it, so you could test a filter with it. And I'd been thinking about testing filters with noise because of, the old modem startup sound. You could hear doo-doo-doo-doo. That noise, you could use that for testing filters. And so the idea was that this thing could be generated through an AWG out to the part, which would be a filter, and then you would see the roll-off directly. And so I wrote up this article on periodic white noise, and it worked great. I did the same thing that I did in my telecom filter test. I generated the periodic white noise, I sent it out through the system without going through the filter, or the device under test, whatever it was, and then I took the reciprocal of whatever the roll-off was, so if it curved down, that meant that it curved up. The reciprocal of that was used to multiply against the frequency domain version of the periodic white noise, and then I'd send it out again. Periodic white noise is it's a coherent version of white noise, so it's absolutely flat, but it doesn't have any, you don't have to do windowing or anything, so it's beautiful. It's a wonderful thing to do, and it's just another example of the stuff you can do with digital signal processing, DSP. So you can look at what I did on DSP on www.danbuller.com/dan/DSP. I did a lot of stuff in DSP, and DSP is my favorite thing. Now, those Falcon 9s don't land themselves. You know how they do that? DSP. Everything that's tested out there, DSP. DSP is taking over everything. And if you don't know DSP, you goddamn well better learn it. Because DSP is the way to go. Anyway, that's it from the river. Thanks for your time.